my name's Kieran Newman. I'm a second year PhD student at National Oceanography Centre and the University of Liverpool. And my talk's on trying to determine tidal phase differences from X-band radar images of wave fields, which is a big mouthful. And what does that actually mean? So I'm going to quickly talk about why phase is important. And it all comes down to methods for accurate high-resolution bathymetry. That's the motivation behind all of this. What's been done so far in this area, where studies have been undertaken, and then a quick overview of my method, my results so far, and some early attempts at validation. So where do we stand at the moment? Basically, that is the kind of image you get out of a radar sat on a mast, an X-band radar sat on a mast in the middle of an island. That's one of the images I'm working with. That itself is actually, I believe, a time lapse. So what do you actually extract from that image? So there's been a method developed by my supervisor and a previous PhD student to take us to these images and extract bathymetry information. So this doesn't show bathymetry directly. The radar's not bounced off the bottom of the sea and give you results back you would with a sonar or something like that. What you're getting from this is wave fields, and you get a strong return at the waterline. So where the waves are breaking at the edge of the sea with the tide going up and down. And the idea behind all of it is if you take the tide at a certain level and you know that the tide is, say, 5 metres above mean sea level, then the edge of that waterline is a contour at 5 metres above mean sea level. And if you take them over a whole tidal cycle, you've got a series of contours running through the whole spring neap cycle, and you can draw contours on and get your beach profile from that. And that's been done for years. That was done with aerial photographs in Second World War, but it's also been done with radar. The method that was previously developed is slightly different in that it shifts from drawing a spatial contour to taking each point and looking at the time series of radar intensity. So if you think the breaking wave line has a very strong intensity signal, okay? So if you have an intensity series for a point, when that point goes from wet to dry, there'll be a sharp gradient change in the intensity signal. So you can take that time and look at a tidal signal to see what time that point wetted and dried, so you then know the height of that point. But the key thing with that is it all relies on a tidal signal. Everything relies on knowing the tide height. And currently they take no account for any spatial variation in tide height. So over an estuary, the tidal height could vary, or the times of high tide could vary. So I'm looking at trying to get phase out of that. So this is an example of some of the steps of the method, but the important one, like I say, is this tidal signal that everything below relies on. And if you don't have an accurate tidal signal for each point, then you're going to have inaccuracies in the method. And the images I'm looking at and the data set I'm using is from the Dee estuary between the Wirral and North Wales, where from 2005 to 2009 there was a radar stuck on a mast up there. So yeah, where do I come in? It's trying to find this spatial variation in water level. As I say, the current method uses a spatially uniform tidal signal over the whole domain. So any differences, local differences in water level or tidal phase differences are going to affect the accuracy of the generated bathymetry. And that's highlighted as the main source of inaccuracy in the paper about that method that's previously been developed. So I started out trying to use some models. They've not worked. I've put them aside. It'd be great if I could run a 5 metre resolution model and get an individual tidal sea level record for every single point. But trying to run a 5 metre resolution model over a whole estuary is difficult. Lots of things don't work. Put that on the back burner. Try and get the signal, the tidal phase, directly from the radar intensity record. So I've got a massive amount of data. I've got hourly averages for 4 years of images over in 1080 by 1024 over this estuary. I've got some at higher time resolution as well. So what I tried doing first is taking a correlation of, for each point, the intensity signal, this wavy line you get out of the radar for that point, and taking a tidal signal and applying a load of lags to it. So basically, if you've got your tidal signal, you apply a lag, so you've now got two tidal signals, one that's 15 minutes shifted, do that a lot, and then take a correlation of that with your intensity signal, and take the signal with the greatest correlation as tidal phase, which is a figure like this, which I haven't put a colour bar on, but the important thing to realise is there's very significant variation, but you can also see some features coming through which, okay, that's starting to look like it could show something interesting. This is a better figure with a colour. So with these figures, there's some bits that start to look quite good. Down the estuary, down here, the difference between, say, there and there is about what you'd expect from the shallow water wave speed of the tide propagating in. So that starts to be good, but in some areas you've got massive lag differences, which isn't necessarily realistic. So what's causing that? How can we improve this? I've got another method as well with, if you take the buoys in an estuary, you're going to have a load of just shipping buoys, marker buoys for channels, things like that. And a buoy will give you a real strong dot on a radar plot. You can see exactly where it is. And if you've got a series of radar plots, you can see that buoy moving back and forth, not too much, but a bit with the tide, because as the tide goes in and out, the buoy's anchored to the bottom of the sea, and the buoy moves back and forth. So you can get a tidal signal or some kind of time series of movement out of that as well, and track this and do the same method, and obviously with you only get points, but you still only get point sources, but you still get some data out of it. Again, it's data, it's showing something. Is it any good? Big question. So I've got various methods to try and validate and improve this. Starting out by using a longer radar record. All that previous stuff was done with a 1 month record of the first 10 minutes of every hour at 2-second intervals, because I was trying to get a very high temporal resolution. But I've got years and years of data. I can take a 6-month record and try and see how that works. So use a 6-month record of hourly averages. So there's some pros of this. It's a longer record, so there's more data to compare. So hopefully the results might be more valid. It might be apply over a longer stretch of time. And the data is evenly spaced. Having the data only in the first 10 minutes of every hour, which was just to do with the storage requirements, when you start to do things to do with time machine and stuff, that starts to get complicated. So having hourly averages gives you nice evenly spaced data. The downside of that is a 6-month record is 52 gigabytes. So trying to do matrix operations on a 50 gigabyte array starts to get computationally expensive. And this lower temporal resolution, because I'm only hourly now. But what you can do with that lower temporal resolution, because you shift the tidal signal and not the radar signal, you can actually resolve phase differences lower, or smaller, than the temporal resolution of your radar data, which is quite handy. So you run this, and you start to get a figure that looks like this, which in a lot of places looks fairly similar to that figure I showed before with the with all the other colours on it. And again, down the main estuary channel here, so the island's in the middle where the radar was. This bit here is the edge of the Wirral, North Wales down here, and there's lots of sandbanks and all sorts of muck around here. But down this main channel, that phase difference agrees to within about an order of magnitude with what you'd expect from the tide just propagating down estuary, which shows there's something maybe to think about with this. But in some places here, you've got 180 degree phase difference in 20 metres, which is obviously rubbish. So I started to think, okay, why is all this weird, massive phase differences coming through? And the answer is, what this is detecting is not the tidal phase. It's detecting the dominant M2 phase in the radar signal itself, which sounds a bit complicated, but basically there's all sorts of things that can affect the phase, the dominant M2 frequency phase of this radar signal. You've got bedform effects, you've got the elevation phase of the tide, and then you've got the velocity phase of the tide, which will also affect this intensity phase, and they're out of phase with each other. And you've also got the wetting and drying signal itself is effectively a binary square wave signal that has its own phase, and all that's getting lumped into this one wiggly signal that I'm trying to pick a phase out of. So I've got 4 or 5 different processes. How do I pick the one I'm interested in out of this combined signal? I've also, because I'm using a correlation method, I can filter by a p-value and cut out some areas where I'm not so confident. But I'll skip over these. So now, trying to pick out which are the dominant processes in this. So I look at how the radar intensity varies by tidal phase and amplitude for each point. So the way to do this is basically it's a take that big record and use a binning method. So take effectively a histogram of it first in phase and then in phase and amplitude. So take the tidal signal, record at each time point what is the phase and amplitude of the tide at that point, and then bin all my intensities, sum the intensities into bins related to that phase. So so produce histograms of intensity by phase alone or by phase and amplitude, which can be compared and analysed, and you get one of these figures for each point. So this weird looking figure for a load of different points in the estuary. So again, you've got the island there, the Wirral there, and these, say 2 and 4 are good ones to look at because they're the opposite side of that bank where there was that 180 degree phase difference. So point 2 is yellow, point 4 is green. You can see point 2 in phase alone has a big skew across to that side, and point 4 has a big skew across that way. So something in that radar signal is picking up a lot more intensity at that phase for the point 2 and at that phase for the point 4. And when you bring amplitude into it as well, you start to get a more complex picture. So again, looking at point 2 and point 4, for example. Again, point 2, you can see this big skew across to the right around the 90 degree phase, and point 4, this more skew across at the 270 degree phase. But there's also other things that start to pop out in this as well, like this dipole formation around 0 and 180 appears in a lot of them, and I think that's bed form induced effects. Not necessarily confirmed yet, but I think that's what's happening. So the aim for all of this is if I can take these points and figure out, okay, the elevation phase is dominating at between these time periods, I can slice that record and only get the bits where the elevation phase is dominant. So these methods could provide a way to determine local tidal phase differences, which could have a direct effect on the accuracy of the waterline method for bathymetry estimation. That's your take-home message. Blair. But to me, the interesting thing is those intensity roses, the things I showed previously. They show some significant variation. There's something different being picked up in all these different points and affecting the phase of the radar. So I've got something interesting happening now. So I'm 2 years in, and now I've got a year and a half to figure out why that's happening. So I'm going to try and carry on trying to use models, but also apply data methods like EOF analysis to these phase roses. And because I've got so much data, I've got terabytes of data, that to me suggests some kind of data-driven approach like a neural network could be a good solution to some of this. So I'm looking at training some kind of machine learning thing with the rosettes as input and bathymetry as output, or as some kind of classifier of, okay, this area elevation phase is dominant and this area it's bed form effects and things like that.